Hello everyone, once again welcome to the video series on the tutorial section of solving the questions in signals and systems from KTU question papers. So we have completed 9 videos so far on tutorials, and the part A of the questions were over. The part A, I can write it as Part A completed include questions from topics like basics of signals, then classification of signals, then signal processing like amplitude operations and time operations. Then we did problems on system basics, then properties of systems. Okay, then we did solving problems on convolution, then impulse response, stability, especially stability and causality from impulse response, and a few questions on autocorrelation. Okay, so these are the topics we have completed, and now we are stepping on to part B questions. Part B questions will cover topics like Fourier series, Fourier transform, Laplace transform, and sampling. Okay, these will be the main topics that will be coming under the part B sections. So let us expect that the upcoming videos will be including problems from these topics. Okay, part B. So this is the first question. Derive the relation between Laplace transform and continuous time Fourier transform. So this is a straight away and a conceptual based question. So the relation between Laplace transform and continuous time Fourier transform. Before let me write down the definitions for Laplace transform and continuous time Fourier transform before stepping into the solution. So Laplace transform denoted by x of s is given by integral over minus infinity to plus infinity if it is a bilateral transform, x of t into e raised to minus st dt. Okay, so this is the definition of Laplace transform, where s is a complex number given by sigma plus j omega. You call it complex frequency. Okay, where sigma is the real part and omega is the imaginary part of that frequency. Okay, that's the definition for Laplace transform. Next is continuous time Fourier transform. Okay, or simply Fourier transform. Okay, Fourier transform is given by x of omega is equal to integral over minus infinity to plus infinity x of t e raised to minus j omega t dt. Okay, so these are the definitions for Laplace transform and Fourier transform. Okay, now let us see what is the relation between Laplace transform and continuous time Fourier transform. So for that, let me take the Laplace transform. Let me start with this Laplace transform. X of s is equal to integral over minus infinity to plus infinity x of t into e raised to minus st dt. I must start from this equation, Laplace transform, and I have already defined what s is. Okay, s is nothing but the complex frequency s equal to sigma plus j omega. So why can't I write s expanded to sigma plus j omega in this equation? That will give you integral minus infinity to plus infinity x of t into e raised to minus of, instead of s I am expanding it as sigma plus j omega into t dt. Okay, now let me expand this exponential, which will give you minus infinity plus infinity x of t e raised to minus sigma t e raised to minus j omega t dt. Is that right? Fine. Okay. Now what I'm going to do is I'm writing this as integral minus infinity to infinity x of t into e raised to minus sigma t into e raised to minus j omega t dt, or I can write it as integral minus infinity infinity some x1 of t into e raised to minus j omega t dt, where what I've taken as x1 of t is equal to nothing but x of t into e raised to minus sigma t. Okay, fine. Now let us see this equation, right? This equation. What is this equation when compared with this expression? In this expression, you can have x of omega as an integral over x of t, some signal into e raised to minus j omega t dt. That is obtained in this equation exactly, right? Some signal, integral over some signal into e raised to minus j omega t dt, and that some signal is nothing but x of t e raised to minus sigma t. Fine. So what is our conclusion? Our conclusion is that Laplace transform, we started with Laplace transform and ended up in this equation, right? Okay, this equation. So what we can conclude is Laplace transform of x of t, Laplace transform of x of t, that is x of s, right? That is this x of s is nothing but the Fourier transform of x of t into e raised to minus sigma t. That's what you can see in this equation. Okay, this is the Fourier transform of x of t e raised to minus sigma t, and that was our Laplace transform. Okay, so this is the link between Laplace transform and Fourier transform. Okay, the next question is evaluate the Fourier transform of x of t equal to signum of t and plot the magnitude and phase response. You know what signum of t is? Signum of t is a signal. Okay, it's a signal like this. Signum of t is 1 for t positive, and it is minus 1 for t negative. Okay, so this is t. So I can draw signum of t as plus 1 for positive side of t and minus 1 for negative values of t. This is graphically signum of t, or we can write it as signum of t is equal to 1 for t greater than 0 and minus 1 for t less than 0. Okay, so what we have got to do is to find out the Fourier transform of the signum of t. Okay, let me give you some tips, some very important tips before proceeding to the solution of this problem. The tips are, actually, you consider this signal, right? This signal, this is x of t equal to e raised to minus some 3t dt. Okay, this signal is a finite, it's a infinite duration signal, but its amplitude is converging. Okay, its amplitude is converging even if it is finite duration. And also we could learn that in the part A questions, we could learn that this signal is an energy signal. Okay, this is an energy signal. For such signals, the Fourier transform could be very simply evaluated by the equation, the definition or equation of a Fourier transform. There is no issue, very straightforward. Okay, now you consider some other signals, like for example cosine signal or sine signal, sinusoidal signals, or u of t, right? What are the specialties of these signals? These signals have a finite amplitude. Okay, finite amplitude, or the amplitude will be within a limit. For in this case, it will be minus 1 less than x of t less than 1. In this case, this is u of t. In this case, the amplitude is always 1 for positivity, right? So these signals are also power signals. Okay, this is a periodic signal. There is always power signal. This signal u of t is a power signal. We have seen it in the part A videos. So for this category of signals, the Fourier transform could never be evaluated from the definition, not from the definition. You cannot play around with the definition of Fourier transform and end up in a valid result. That will be wrong. Okay, so what we have got to do is to calculate Fourier transform for these signals, for these power signals, we have to make use of some tricks or some logics or some properties. We can never use the equation or the definition of Fourier transform to evaluate it for these kind of signals. But for these kind of signals, it is very simple, it's straightforward. You can use the definition of Fourier transform. Okay, and we have also one more category of signals. For example, e raised to 3t u of t. It is to 3t u of t. I don't know why did I mention dt here. It is u of t. Okay, so what is the nature of e raised to 3t u of t? It will be a signal which is exponentially growing. Okay, and now these signals are not finite. Okay, these are infinite signals, infinite in case of time as well as amplitude. Okay, so these signals are neither energy signals nor power signals. Okay, and now listen, for such signals Fourier transform will not exist. Okay, for such signals Fourier transform cannot exist. So these are the three categories. Just consider this as a tip or some capsules before solving the problems based on Fourier transform. Okay, so keeping these points in mind, let us try to solve this question to find the Fourier transform of x of t equals signum of t. So like I said, you cannot use the expression for Fourier transform to evaluate this signal, evaluate the Fourier transform for this signal, because the signal is an infinite duration but finite, a marginally stable signal. Okay, so I have to apply some trick. Okay, what I'm going to do is I'm going to write signum of t as this is the trick I'm going to do. Limit a tends to 0, okay, e raised to minus a mod t into 1 for t positive and minus 1 for t negative. Okay, will I change anything from the definition of signum of t? Can I write or equate signum of t as this? Okay, actual definition was this one, but I have introduced something extra here, multiplied something extra here. Will that be invalid? No, that won't be invalid because e raised to minus a mod t, but you can see the a here is tending to 0. So this is practically e raised to 0, 1. So I'm multiplying this signal or this signal with 1, essentially 1. So that is not gonna make any difference to my actual definition. Okay, so I can safely move around with this equation. Now let me remind you what is mod t or e raised to minus a mod t. Actually, I can write somewhere else here. This is rough space. So e raised to minus a mod t is equal to e raised to minus a t for t positive and e raised to plus a t for t negative. Again, this was dealt with some problems in the part A videos. Okay, so this is the definition for e raised to minus a mod t. Okay, now I'm using this expression, this result, in developing this this equation. Okay, so that implies signum of t is equal to limit a tends to 0. Okay, now I am going to multiply this signal with this portion where t is greater than 0, and you know at t greater than 0 e raised to minus a mod t will end up in e raised to minus at. Okay, so this signal will be e raised to minus at when multiplied with this portion, this half. Okay, so I am writing it as limit a tends to 0 e raised to minus at for t greater than 0. And now what I'm going to do is I'm going to multiply this portion with this this portion, right? And you have to take care that e raised to minus a mod t will reduce to e raised to plus at for t less than 0. That means this portion. Okay, so I can write this as minus 1 into e raised to plus at for t less than 0. Okay, so this is what we are going to end up with while manipulating signum of t like this. Okay, now we can move forward with this expression to find the Fourier transform. Now I'm going to find the Fourier transform of signum of t, which is equal to now I can apply the formula, right? We are not directly applying the form definition for Fourier transform to signum of t, but we are going to apply Fourier transform to this equation. Actually, will this equation, or will our approximation limit a tends to 0 e raised to minus a mod t affect the signal in any way? We have mathematically seen it will not affect it in any way, but let us see it graphically also. Our signum of t is like this, right? And so we are applying e raised to minus at. Actually, we are multiplying with e raised to minus at. You know what e raised to minus at is? E raised to minus at in t greater than 0 will be a decay exponential, right? But the decay, right, the factor which determines the rate of decay a is approximately 0. That means it does not decay at all. Okay, so instead of giving a decay, it gives a straight line. The same happens in this case also. Okay, right. So let us resume the equation. Okay, so limit a tends to 0. First I am going to take this part. Okay, so integral, actual definition is from integral minus infinity to infinity x of t e raised to minus j omega t dt. That is the expression for Fourier transform. Okay, but here we have two parts, this one part and this two part. Okay, so I'm considering this part first. So this is negative t, so minus infinity to 0. Okay, minus infinity to 0. We have minus e raised to at, right? This is the signal in negative t axis. So minus e raised to at into e raised to minus j omega t dt. Okay, plus the next part is again limit a tends to 0. Next is this part, positive part. Okay, so 0 to infinity, and in that case the signal is e raised to minus at. Okay, so signal into e raised to minus j omega t dt. That's the definition, signal into e raised to minus j omega t dt. All right, now let us expand this. That is limit a tends to 0. I can write minus infinity to 0. There will be a minus. I'm taking this minus outside. So this becomes e raised to a minus j omega t dt plus again limit a tends to 0, integral 0 to infinity. I can write this as e raised to minus of a plus j omega t dt. Right. So this is equal to, now I can integrate limit a tends to 0 minus of, what is the integral of a minus j omega into t? It is e raised to a minus j omega into t divided by a minus j omega within the limits minus infinity to 0. Right. Plus I'm going to do the same with the next term. Limit a tends to 0. What is the integral of e raised to minus of a plus j omega into t? is e raised to minus of a plus j omega into t by minus of a plus j omega within the limits 0 to infinity. Okay. Okay, let me get some more space. So that is equal to limit a tends to 0 minus 1 by a minus j omega into, now we can apply the limits. While we apply the upper limit, it is going to be e raised to 0, that is 1, minus, and now when we apply the lower limit, it is going to be e raised to a minus j omega into minus infinity. So it is e raised to minus infinity, and you know e raised to minus infinity is 0. So this is going to be 0 plus, next term is limit a tends to 0 minus 1 by a plus j omega into, now we are going to apply the limits. So the upper limit is infinity, but here it is e raised to minus something into infinity is e raised to minus infinity, that ends up in 0 minus, and while we are substituting the lower limit, it is e raised to 0 as 1. Okay, so this is equal to limit a tends to 0 minus 1 by a minus j omega into 1 plus limit a tends to 0. This is minus 1 here, right? So minus 1 becomes plus 1 by a plus j omega. Okay, now let us apply the limits. Limit is from a tends to 0, limit is a tends to 0, so that implies Fourier transform of signum of t will be equal to, when we give 0 here, it is minus 1 by minus j omega, that is 1 by j omega plus 1 by j omega, plus when you substitute 0 here, it is 1 by j omega, so that is 2 by j omega. Okay, so this is the ultimate expression for the Fourier transform of signum of t. Okay, and the next question is, an LTI system is characterized with the transfer function h of s equal to s plus 5 divided by s square plus 3s plus 2. Find the response of the system to the input x of t equal to cos 2t u of t. Okay, so whatever be the h of s, x of t values, the ultimate thing you need to know is this is an LTI system. So if h of s is the transfer function of that LTI system, and if x of s is the Laplace transform of the input to that LTI system, then the response or output of that system will be y of s equal to x of s into h of s. This is the most important thing you need to note here, and actually that comes from our part A knowledge, that y of t of an LTI system will be x of t convolution h of t, and you know the convolution property of Fourier transform and Laplace transform, that will be equivalent to multiplication in Laplace domain or Fourier domain. Okay, so we are provided with h of s is equal to s plus 5 by s square plus 3s plus 2. Oh, I can write it as s plus 5 divided by s plus 2 into s plus 1. You can always write the denominator as a factorized form, that will be easier for the calculations. So that is h of s. Okay, now we have to find x of s also. X of t is given as cos 2t u of t. Okay, then what is, using the knowledge in Laplace transform, or you can study it as a result, if cos 2t u of t or if cos at u of t is the signal, its Laplace transform will be, what will be its Laplace transform? It will be s by s square plus a square. Okay, so here it is cos 2t u of t, so x of s will be s by s square plus 2 square, that is 4. Okay, so we got we have h of s and x of s. Now what is y of s? Therefore from this expression, y of s is equal to x of s into h of s, which is given by s by s square plus 4 into s plus 5 by s plus 2 into s plus 1. I have multiplied listen, s by s square plus 4, that is x of s into h of s. Okay, and now what is this? This can be actually now okay so we got y of s. Our question is to find the response of the system. Response means it is a signal, is in time domain. Okay, so we have got the Laplace transform of the response in this expression. Now what we got to do is find the inverse Laplace transform to find y of t. Okay, so before finding inverse transform, we have to make this as a partial fraction. Now listen, I don't, while making partial fractions, I don't have to mind what is in the numerator, whatever it is. I don't know, I don't care, but we have to take care of the format of the denominator. Denominator is in the form s square plus 4 into s plus 2 into s plus 1. So here a term consists of second order, so I can write it as as plus b by s square plus 4. You know, s square plus 4 term has degree or power 1, right? No, power 2. So in the partial fraction I have to use as plus b, 1 power less. Okay, square, but here it is s. All right, plus c by s plus 2. This is for this factor, and for the final factor it is d by s plus 1. Okay, d by s plus 1. Now let us take the LCM. Then you will get as s into s plus 5 will be equal to as plus b into s plus 2 into s plus 1, right? Then c into s square plus 4 into s plus 1 plus d into s square plus 4 into s plus 2. That's what you will get. Okay, now what you have to do is these values a, b, c, d are introduced by ourselves. So we have to find the values of these constants without changing the expression, right? Without changing the value of the expression. So what we have to do is we can just expand this. X square plus 5s will be equal to while expanding this term, I can write some words as it is as plus b into s square plus 3s plus 2. Okay, that is as cube plus b square plus 3a square plus 3bs plus 2as plus 2b. Okay, right, so I can write it here clearly. A is cube plus b square plus 3a square plus 3bs plus 2as plus 2b. Okay, so that's what you will get when you expand this term, right? Now plus now I'm going to expand this term. So what you will get is c into, I can write somewhere here, c into what is the expansion of x square plus 4 into s plus 1? You will get s cube plus 4s plus s square plus 4. Okay, so multiplying c with this expression, you will get cs cube plus 4cs plus cs square plus 4c. Okay, then now I'm going to expand the next term, this term. Okay, so that will give you I think again I can write for convenience here, d into s cube plus 4s plus 2s square plus 8. Okay, so that will become ds cube plus 4ds, right, plus 2ds square plus d8 or 8d. Okay, right. Okay, so I have expanded this. Now our aim is to find out the value of a, b, c and d. Okay, for that what I'm going to do is you have to find a, b, c, d by equating the coefficient of LHS and RHS, power of SN, LHS and RHS to be precise. First let me take equate the coefficient of s square. Equate the coefficient of s square on both sides of the equation. In LHS you can see the coefficient of s square is 1. So 1 is equal to, and in RHS you can see b, right, b plus 3a plus c plus 2d, right. These are the coefficient of s square in RHS. Now we can equate the coefficient of s cube, maybe, right, s cube on both sides. So what is the coefficient of x cube in the LHS? There is actually no term in LHS having s cube, so it is 0 equal to. Now let us find out the coefficient of s cube in the RHS. We can have a plus, then comes c, then d, that means, right. So 0 equal to a plus c plus d. What should be next? Next can be equating the coefficient of s on both sides. Okay, so what you will get here in LHS, 5 is the coefficient of s, and in RHS there will be lot many terms, 3b, right, 3b plus 2a, okay, 2a. Now 4c comes, plus 4c, then 4d is there, that much, right. So 5 equal to 3b plus 2a plus 4c plus 4d. And finally we have one more chance. We can equate the constants. I can write k here, constants on both sides. Okay, what is the constant of LHS? There is no constant, that means it is 0. Okay, so 0 equal to, now let us see the constants or terms without any powers of s in RHS. So those come as here. Okay, 2b is a constant term, it doesn't have any s in it. Then 4c is another one, 4c, and finally 8d. Okay, or I can write it as 0 equal to b plus 2c plus 4d. So these are the 4 equations we have in a, b, c, d. So 4 variables, 4 equations. You can find the value of a, b, c and d using many methods. You can maybe you can have your calculators which can process 4 equations and 4 unknowns, or you can eliminate variables. That would be a tedious process, or we can use a matrix like Cramer's rule or raw reduction in echelon form. You can have many ways to obtain the result. So I think I will straight away write the answer from my calculations. So what I have calculated is you will get a equal to, because calculating this in all the procedures will take many time, right, much time. It will be very lengthy procedure. So I'm straight away giving you the answers. A equal to 1 by 20. You will get a equal to 1 by 20. B equal to 17 by 10, right. Then C equal to, it will be 3 by 4, and D comes to be minus 4 by 5. Okay, this will be values of A, B, C and D. Okay, now you have to listen carefully. So we have we posited this equation, right? This equation where we had A, B, C and D in our hand, and now that we have got the values of A, B, C and D. Now put these values in the equation. Okay, therefore S into S plus 5 by S square plus 4 into S plus 2 into S plus 1 will be equal to AS plus B. A is 1 by 20, S plus B is 17 by 10 over S square plus 4 plus C by S plus 2. C is 3 by 4. So 3 by 4 into 1 by S plus, you can write like this, plus D is minus 4 by 5. So it is minus 4 by 5 into 1 by S plus 1. Okay. Now we have got to find the inverse Laplace transform in RHS. So for that I can write it as, so this is one, I am separating the first terms, these terms, right? There are two terms on the numerator. I am separating it. 1 by 20 into S by S square plus, I am writing it as 2 square for some specific purpose, plus now it is 17 by 10 into 1 by S square plus 4. I am writing it as 17 by 20 into 2 by S square plus 2 square. Again, for some specific reasons, right? You can see I have it was 17 by 10 actually, but I wrote 17 by 20, and to cancel it I have multiplied 2 with 2 in the numerator. Okay, and now the third and fourth terms will be like that: 3 by 4 into 1 by S plus 2 minus 4 by 5 into 1 by S plus 1. Right. Now from the above equation, you might be thinking, many of you might be thinking, why I have written this in a weird way, but it is for the reason that all the terms in the RHS in this equation are in known or defined Laplace transform expressions of defined signals. Okay, this is S square, S by S square plus 2 square, whose inverse transform will give you cos 2t, right? S by S square plus A square, so it is cos 2t. This is 2 by S square plus 2 square, which gives you, whose inverse transform will give you sin 2t. Okay, this is the Laplace transform of e raised to minus 2t, and this is the Laplace transform of e raised to minus t. Okay, now it's only a matter of completing that equation. Therefore y of t is equal to 1 by 20 into inverse transformers. I have told you it is cos 2t plus 17 by 20 into the inverse transform of a by s square plus a square is sin 80. So here raised to, so sin 2t plus 3 by 4 into 1 by s plus 2, the inverse transform will be e raised to minus 2t minus 4 by 5 into e raised to minus t, the whole into e of t. So this is the final answer of this question. Okay, the next question is, state sampling theorem, calculate the Nyquist rate of the signal x of t given a signal. Okay, so sampling theorem is one of the most beautiful theorem in signal processing. So it states that you have to refer the textbooks, standard textbooks, for the complete definition, complete understanding. Anyway, I am just giving you a superficial idea about sampling theorem. Sampling theorem states that a band limited signal, right? A band limited signal. A band limited signal means it is a signal which contains a frequency component, a maximum frequency component, and nothing over that, above that. Okay, so a band limited signal can be sampled. Okay, fine, but it can also be retrieved from its samples faithfully without any errors. Okay, only when the sampling frequency fs is greater than at least twice, greater or equal to at least twice the maximum frequency component of the message signal. Okay, where fs is the sampling frequency, fm is the maximum frequency of the message signal. That is what sampling theorem says. Okay, now this Nyquist rate, this 2fm, or the maximum value of the minimum value of the sampling rate, sampling frequency, is called the Nyquist rate. 2fm is the Nyquist rate. Okay, so we have to identify what fm is. Fm is the maximum frequency component in the signal, message signal. So multiplying that value with 2 will give you the Nyquist rate. Okay, so our signal is x of t is equal to cos pi by 2t minus sine pi by 8t plus cos pi by 4t plus pi by 3. And never get scared of this phase shift and all. It is not going to affect our answer because we are interested in the frequency components in the signal. Actually, there are sum of three sinusoids. So there are three frequencies in the signal. What are these frequencies? First frequency is omega by 2. Pi by 2. Okay, pi by 2. Second frequency component is pi by 8. Okay, coefficient of t will give you omega. Okay, omega pi by 8, right? And the third frequency is pi by 4. Okay, so pi by 2, pi by 8, and pi by 4. So which is the maximum frequency component? It is the maximum value. It is pi by 2, right? So we can say that maximum omega is pi by 2. You know, pi by 2 is greater than pi by 8 and pi by 4. This is very basics, right? So omega m is pi by 2. Therefore, what is fm? Fm is the relation between omega and frequency. Omega is angular frequency, f is linear frequency. So these are linked by omega equal to 2 pi f. And what is f? Therefore, f is equal to omega by 2 pi. Okay, so fm is equal to pi by 2. Omega m divided by 2 pi. That will give you 1 by 4. Okay, so fm is equal to 1 by 4. So what is Nyquist rate? Nyquist rate is nothing by 2fm, right? 2fm. Therefore, Nyquist rate fs is equal to 2 times fm, that is equal to 2 by 4, that is 1 by 2 hertz. Okay, that's the final answer.